Okay, so the next thing I want to point out in radial quantization, which is rather interesting, is let's look at the dagger of the dilatation operator. So this will be equal to inversion, d dagger inversion. And we know that in Minkowski spacetime, the dilatation operator is Hermitian. So this will be I di. And then it is in one of the exercises that I ask you to compute what inversion dilatation operator inversion is. So it's straightforward to do. It's not a difficult exercise. And you'll find that this is equal to minus the dilatation operator. So what that tells you is in radial quantization, the dilatation operator has imaginary eigenvalues. It's anti-Hermitian. So it has imaginary eigenvalues. That's rather interesting. Okay, what it also suggests is we could study I times by d. Why is this nicer to study? Well, if you take ID star, you can easily check this as ID. So this has got a real spectrum. So that's why it's nice. If you want to study an operator with a real spectrum, instead of studying D, study ID. Okay, now let me make the point I wanted to make. So this is really the point I wanted to make. I keep telling you that radial quantization is an extremely powerful picture with which to study conformal field theory. Why is it so powerful? Well, I'm going to give you one of the really good reasons now. I want to go back to the algebra that we calculated, and we worked out that I times by d, commutator with p mu, was equal to p mu. And we also worked out that I d commutator k mu was equal to minus k mu. And notice that here we've got ID. This is a Hermitian operator. So Hermitian operator. And even more than that, we said that we wanted to know the eigenvalues of the dilatation operator. So we wanted to know the eigenvalues of ID. And the other thing that we've got P mu star is equal to K mu, and K mu star is equal to P mu. Okay, now I want to remind you of something because you've seen this structure before. So let me put this, the structure that I want to remind you of. And what do I want to remind you of? I want to remind you of the harmonic oscillator. When you studied the harmonic oscillator in quantum mechanics, the thing that you wanted to figure out was what was the spectrum of the Hamiltonian. And then you used this very clever trick due to Dirac. And Dirac introduced the creation and annihilation operators. And what was important is that the commutator of the Hamiltonian with the creation operator was a dagger, and the commutator of the Hamiltonian with the annihilation operator was minus a. H was Hermitian, so H was Hermitian, and it was the thing whose spectrum you were trying to figure out. And we know how a dagger and a are related. If you take a and you dagger it, you just get a dagger. And if you take a dagger and you dagger it, you just get a. So what you see written in black is a complete analog of what you see written in blue. The algebraic structures are the same. So whatever we use to solve the harmonic oscillator problem written in black, we can use that same logic to solve the problem written in blue. Now, for the harmonic oscillator, we figured out how to determine the spectrum of the Hamiltonian, so we'll be able to use the same method to figure out how to determine the spectrum of the dilatation operator. And remember what we did for the harmonic oscillator. We said, let's define a state which is annihilated by A. And this was the ground state. That's what we called it. And it was the state of lowest energy. Lowest energy. And then to create all of the other states, we defined the state n, which was equal to a dagger raised to the power of n acting on the vacuum. So not normalized now, but these were the states of higher energy, higher energy. Well, in the conformal field theory, we do something completely analogous. So this is what we do in the CFT. We take K mu. So K mu is the special conformal generator. It plays the role of the lowering operator. We allow K mu to act on O, and we look for solutions to K mu on O is equal to naught. We don't call these ground states anymore. We call them primary operators. And one difference to the harmonic oscillator is that when you solved for the ground state, you found a unique ground state. Actually, in the conformal field theory, you will find many different primary operators. And in fact, it's a challenge to work out what is the complete set of primary operators. Now, the ground state is the state of lowest energy. A primary operator is a state of lowest dimension. One of the things that you would love to work out, it would be incredible if you could work this out, would be if I give you a conformal field theory, you work out the complete list of primary operators and the dimensions of each of those primary operators. That would be remarkable if you could do that. Now, once you've got the primary operator, again exploiting the analogy to the harmonic oscillator, we can create states of higher dimension. How do we do that? Well, we use the analog of the raising operator, which was the momentum operator P mu. So we could act with P mu 1, going all the way up to, say, P mu n. So we'll act with a total of n different P mu's, all on the state O. We call these descendant operators, and we would say that they are descendants of O, the primary O. And these have a higher dimension. In fact, if the primary had dimension delta, so delta's the dimension of the primary, then the dimension of this descendant, the dimension would be delta plus n. So every time you act with P mu, you increase the dimension of the descendant by 1. So you add 1 to the dimension. Now, so in fact, what you can do is you can organize the entire Hilbert space. Remember, we said the local operators give you a Hilbert space structure. You can organize that entire Hilbert space structure into a collection of primary operators together with their descendants. And these primaries, together with the descendants, will actually span the complete Hilbert space. And it turns out that this organization is very useful. When you were studying quantum mechanics, if you were doing rotations, you could mix a spin 2 state with another spin 2 state, but a rotation could never mix a spin 2 state with a spin 4 state. Conformal transformations can never mix descendants or primaries which are different. So if I've got two different primaries, there's no conformal transformation that will mix them. And if I've got descendants of different primaries, there's no conformal transformation that can mix them. So what a conformal transformation can do, it can mix different descendants of a certain primary. It can mix the primary with its descendants. So that's what conformal transformations can do. This is the analog of the statement that in a Poincare invariant theory, Lorentz transformations can mix 4 vectors with 4 vectors, but it could never mix a 4 vector with a scalar, and it could never, say, mix a 4 vector with a fermion, a spinor representation. So you can only mix the same representations of the Lorentz group by a Lorentz transformation, so states that belong to the same Lorentz representation will mix. Here too, states that belong to the same conformal representation will mix. And the complete conformal representation is given to you by the primary operator together with all of its descendants. Now, this structure that we found relied crucially on being on the plane and on doing radial quantization. because it's only in radial quantization that P mu dagger is equal to K mu. And we needed that to make the analogy between A and A dagger of the harmonic oscillator. So I hope this discussion at the end has convinced you that radial quantization really is something that's very useful for CFT. I hope you can start to glimpse why it's so useful. We'll be studying primary operators in a lot more detail in what follows, and their descendants and their transformation laws. And that brings us to the end of this lecture 3.